where were we? So we discussed that we cannot add num-v and closure v, right? Previously, we were evaluating an addition of 1 plus x. In the function body, it was like what? That's the parameter, and 1 plus x. And 1, num-v, x, that's the value of the parameter. When we have a function call before, it was with argument 10. And that was not num-v10, but x per v. It was x per v with not num-v, but num10 and the environment. And when we evaluate the function body, one's value is num-v, x's value is, look up the environment, which is x per v. So we couldn't add num-v and x per v. And now what can you do? When we have two values, we'd like to have num-v and num-v. Do you remember what kind of values we have in LFAE? We have three kinds of values: num-v, clo-v, and x per v. And here, num-v is for number, closure v is for closure, and x per v is not actually a value. It's not a value. It's a what? Placeholder. It's a freezer. It freezed an expression and an environment until when it is necessary. Addition is the place when we need the value of x. So we are going to say melt it. The frozen value should be melt here. That's called strict. That's the name of our function. Strict is the magic function to, hey, evaluate it now. We need the value now. That's strict. We are going to define the strict function in a minute. And let's just assume that strict function takes a value, right? It takes a value and then either get to num-v and closure v or what? Nothing. We need to get the value down, meaning that it takes a value which is either num-v, closure v, or x per v. If it's num-v, that's good. It's already a value. If it's a closure v, that's good. It's already a value. If it's x per v, evaluate it. That's the strict function. We're going to see the definition in a minute. When we call when you call this strict function on the value, then we're going to get the value down, num-v or closure v. If they are two numbers, right, then we can perform the addition or subtraction. Otherwise, error. Okay, what's a strict? This is the strict function. Again, the strict function takes a value, produces another value. But this time, the input value could be num-v, closure v, or x per v. But the result value should be num-v or closure v, no x per v. Are you with me? Yeah, you need to understand this. So one more time, when we have a value, we're going to say, hey, are you x per v or num-v or closure v? It's a num-v or closure v, that's good. That's already a good value. If it's x per v, that's not a real value. We need to evaluate it. We need to interpret that captured expression under the captured environment, get the value, okay? But the question is, why this nested strict function call? Do you see that? Why? Why? Because x per v may capture another x per v. Meaning that x per v may have x per v in it. Okay? Okay, so this is my challenge to you. Write down a concrete expression. Say, this is kind of concrete expression. X is 1 plus x with 10. Here, when you evaluate this addition, that strict calls, they're gonna call on this num-v and x per v. But when you evaluate this x per v with this strict function, you may not need this strict function. But write down another concrete expression that requires this strict function, meaning that without strict, this nested strict function call, you are not going to get down to non-v or closure v, but yet another x per v. Let me repeat this in Korean and again in English and move on. 이거 중요해서 한국말로 한 번 더 해요. 지금 이 strict 함수 정의하는데 nested strict function 콜이 있네요. 어째서? 어째서 그럴까요? 이 concrete expression은 이 nested strict function 없어도 상관없어요. 이런 비스무리한 concrete expression 한 번 더 만들어 보세요. strict function이 nested strict function 콜이 꼭 필요한 example. 오케이? 그렇게 만들 수 있으면 이거 이해한 거예요. You should be able to write down a concrete expression that requires this nested strict function call. If you can make that concrete expression, meaning this kind of in syntax of LFAE, not in abstract syntax, okay? Then you now understand what's going on with this laziness and strict function call. Then, what is it? What is this strict function call for? That's to enforce when to evaluate the frozen expression. The strict function call here, these two, that signal that we need the actual value, not x per v, but real value. Why? Because we need to perform this arithmetic operation, plus or minus. Okay? Again, there are three kinds of values in this LFAE language: non-v, clo-v, and x per v. Again, x per v is not a real value, so when we have x per v, we need to strictify and make it real values. When do we need to do that? When do we need non-v? Addition and subtraction. That's why in non-v operation we called strict function. What else? There's one more place for closure v. When do we need closure v? When should we call this strict function for closure v? When do we use closure v? Meaning, when do we look up the value of clo-v? Look up the value of clo-v. What do we have in clo-v? Parameter, body expression, and the environment. When do we use them? Do you see that? You should be able to answer this question. When is it? Yeah, function call. Okay? It's really important. There's a reason that I emphasize that multiple times. One more time. As usual, function call is the key. 뭔가 새로운 애가 나오면 함수 콜이 언제나 제일 중요한 expression이에요. Whenever we have a new concept like mutation, call by value, call by reference, and laziness, function call is the most important language construct. Why? Because everything is function call. Remember lambda calculus? Yeah? Everything is identifier, function call, and function expression. So function value and function call, especially function call, is the most important thing in many cases. Again, in this laziness, function call is important in a sense that, the previous implementation was wrong. Okay, it was wrong in the sense that when we interpret just first of expression, there could be, again, three cases: non-v, closure v, and x per v. If it's non-v, it's an error. That's good. If it's x per v, it should not be an error. Yeah, look at that. If we didn't have strict function as before, 아까 strict function 없었잖아요. 그거 틀린 거예요. 그죠? If we do not have this strict function call here, then when we have x per v, we're gonna get to here, it's gonna be an error. That's not the semantics we want. What we want is to strictify this x per v. Hey, this first of expression that's supposed to be a function that's not yet evaluated. Okay, so we need to call this strict function to, hey, melt it. We need to get its value. If it's still non-V, that's an error. But if it's closure V, we can evaluate the expression. Okay? That is the semantics. Meaning that where to call this strip function is the key to the laziness. We are going to get that point at the end of today's lecture. Until then, we call strip function in what? When we actually needed those values. When do we need non-V? Addition and subtraction. When do we need closure V? Function call. When we need those values, at that point, we cannot defer anymore. We cannot be lazy anymore. Then strict. Call strict function. Okay? Are you with me? So far, so good? Then let's move on to the second point. What? The main motivation behind laziness is what? Being lazy. Meaning that we do not want to evaluate the argument expression if that's not being used. 써먹지도 않을 argument expression은 계산 안 할래였어요. 똘똘한 척하고 했다가 지금은 속는 거예요. 똘똘한 척하다가 망하는 거지. We want it to be smart. We want it to be clever in the sense that we don't want to evaluate the expression, the argument expression. If not, that's not going to be used. But look at this example. What? This parameter is being used multiple times. If it was FAE, we are going to evaluate this the argument expression only once. In LFAE, we are not going to evaluate this complex expression in the function call site and freeze it using X per V. And then pass that to the function body. And whenever we encounter this parameter, we're going to look up the environment, get the X per V, and melt it multiple times. How many times is 8 plus 9 evaluated? 1, 2, 3, 4 times. Since the result is always the same, we'd like to evaluate this expression just once. At most once meaning what? If it's not being used, we are not going to evaluate it. If it's going to be used, we are going to evaluate it just once. That's what? Reducing the redundant evaluation. We evaluate the same thing multiple times. That's redundant. 그죠? We'd like to be more clever again. How? By caching it. Remembering that. Yeah, right? When we have this complex expression, we'd like to evaluate that once. At most once. And when we need to evaluate it multiple times, get the value. How? By using this option type. You should be familiar with this option type by now, but let's review one more time. An option type represents optional values. Instances of option are either an instance of some or the object none, meaning that this option type has a type parameter and then it captures this optional case, like it either nothing or it has something. You'd better take a look at this document. And how do we use is this. You've been using that for multiple times by now, but let's see one more time. Option is a type constructor that takes a type argument. So meaning that it's going to be either nothing, none, or some with the value. And now that we have this type, the value in sum should be integer. That's option type. And by using this option type, we can cache the result. We can cache the value. How do you do that? So instead of keeping this expression and an environment in X per V, we have the third field for caching. Caching strict results. So, as before, this X per V captures an expression, the argument expression, to evaluate later when that's being used, and an environment when that's gonna be, that's being used at the function call site. And then it's a variable, meaning that the value of v can change. How? In the beginning, it's going to be nothing, right? And when we have the value, we are going to replace that non-value with some value. That's the trick. So previously in strict function, when we have x per v, we just interpreted this argument expression using that environment. And then because the value could be, against x per v, we had to strict it. That's the previous version. And now new version is a bit slightly more complex because we'd like to cache that. Meaning that, hey, you value, are you x per v or not? Because the value, one more time, the strict function takes a value which could be num-v or closure v or x per v. And the result should be num-v or closure v, no x per v. Because strict meaning get rid of that x per v. Get down to num-v or closure v, right? So if the input is already num-v or closure v, we are going to return it as it is. If it's x per v this time, it has an expression, an environment, and the result. Okay, the result of expression. So the result is what? That's option of value, meaning that's going to be either none or some. Right? Do you see that? The value, the result is either has some cached value or not, meaning that it's already evaluated. This expression is already evaluated and we know the value, which is this cached value. Then, what do you think? Just get it, right? If this x per v was already evaluated, then that's going to be stored in here. It's going to be option value. So if the value is already evaluated, then it's going to be captured as a sum with the value and we can return the value as it is. Otherwise, meaning that this is the first time that we are evaluating this expression. It's the first time. What can we do? Yeah, then evaluate it right away. Evaluate the second sub-expression, evaluate the captured expression under the environment, and because that could be again, x per v, strict it, nested function call of the strict. Then get the value cache. Are we done? If we are done and just return cache, then what? This x per v didn't change and we are going to evaluate that one more time. And many other times. So we need to store the evaluated result. Do you see that? Do you see it? One more time. We have x per v. This is an expression to evaluate under this environment. And yeah, this is a cache. If we already evaluated the expression, then look up, get the result out of that. Yeah, that result will have this some value and get it. If not, this is the first time we are evaluating that expression, get the value, and this is the first time. So when we evaluate this expression later, we need to look up this cache. So we need to change that. Change what? We need to change the third component of this x per v. That's why we gave it a name. Do you see it? So let's see. So we are gonna change the third field of EV like this. We are gonna change the third value of EV with this computed result. Ooh. You should be able to understand this one single line. Let's see one more time. When we have this strip function call, we look up the value, argument value, and see whether that's X per V or not. If it's X per V, let's name the whole thing, because we are going to call it. We are going to use this value later. So we give that a name EV. EV is this whole thingy. EV is the whole value. This is the Scala syntax to give a name to this value. EV at this value. And then we are not going to use this name if it's already cached, because we are going to just use the value. Otherwise, we are going to evaluate this expression under this environment. And because this is none, we need to replace that with sum with this newly evaluated result. How do we do that? We named it EV, which is X per V, which has three fields, E, EMV, and V, right? So we can name the third field by EV.V, and then we can change its value to new value because that's a var variable. So far so good? Yeah, it should not be news to you because we have been using this syntax by now, right? And then what's the last thing to do? Now that we evaluated the expression and get the value, now that we store the value for the future use, we can just return the result, and that's it. Do you see that? Yeah. So we are gonna get back to this interpreter code after the second break, but let's emphasize the use of environment here. So the thing is, when we have this function, parameter, and body expression, this is a function expression, right? And then when it's been called, we have some argument expression. Because it's a lazy evaluation in this function call, we didn't evaluate this expression. We didn't evaluate this argument expression. Just capture that as it is as X per V with this argument expression. And then environment at the time with this value that we are going to see after the second break. And the point here is that this environment is the environment at this function call. Because when we encounter X in B, this is another body expression, and we may use X multiple times there, right? And X's value is going to be, by looking up the environment, this X per V. At that point here and there, their environment are going to be different, right? They may be different, but evaluation of this expression E should be with this environment. That's why we captured this environment. And what's going to be the third component? We are going to discuss that after the second break.